These are the answers to the Chapter 4 practice quiz that covers sections 4.1 to 4.4. Starting with the multiple choice section, number 1. This particle diagram has 4 cations and 8 anions. So therefore, we're looking for a compound that has a 1 to 2 molar ratio between its cations and anions. Here are the formulas of the 4 choices. We have calcium chloride, magnesium oxide, potassium bromide, and sodium sulfide. So the only compound that has a 1 to 2 ratio between cations and anions is A, calcium chloride. Number 2 is asking us to choose a reaction that explains what happens when ammonium nitrate dissolves in water. You should know that ammonium nitrate is an ionic compound, and so when it dissolves in water, it simply breaks up into ammonium ions and nitrate ions. Nothing else is going to happen that's going to form ammonia or anything else, so you're simply going to show the dissociation of ammonium nitrate into the cation ammonium and the anion nitrate. Correct answer is B. Number 3, we have some laboratory data about this mystery compound reacting with potassium sulfate and reacting with silver nitrate. If it reacts with potassium sulfate and forms a white precipitate, we know that alkali metal cations are soluble, so the white precipitate is not going to be potassium anything. It's going to contain sulfate. Let's look at the solubility rules. Insoluble sulfates could be strontium, barium, mercury, or lead sulfate. So when we look at the 4 choices, we can eliminate choice B, sodium bromide, because sodium sulfate would not be a white precipitate. But barium, lead, and strontium would be a precipitate. So far, A, C, and D are all potentially correct. Let's move on to the formation of a white precipitate with silver nitrate. We know from our solubility rules that all nitrate compounds are soluble. So therefore, if there is a white precipitate, it's not going to be nitrate. It's going to be something with silver. So we have potentially a precipitate with silver chloride or bromide or iodide, silver sulfide, hydroxide, carbonate, and phosphate. So let's take a look at, could it be silver chloride? Yes. Could it be silver carbonate? Yes. But it could not be silver nitrate. So we can eliminate choice D. Now we have to remember that compound X is an ionic compound that is soluble in water. Lead carbonate is insoluble in water. So the correct answer for number 3 is A. Number 4 is asking us to make a prediction about the formation of a precipitate. And we have 4 choices. We'll start with the solubility rules. It looks like nitrate and acetate are soluble. So in choice A, mercury nitrate and silver acetate would not form a precipitate. Then we have in choice B either zinc sulfate or aluminum chloride. But since both of those compounds are soluble, there'd be no precipitate with choice B. In our next example, we have potassium and lithium, which are both alkali metal salts, so there's no precipitate there. The precipitate would be with sodium iodide and lead nitrate. The precipitate that would form would be lead iodide. In number 5, we have particle diagrams to show us what happens when solutions of silver nitrate and magnesium chloride are combined. If we look at beaker X, all of the choices have 2 molar silver nitrate, but some of the choices have either 2 molar magnesium chloride or 1 molar magnesium chloride. The particle diagram should tell us the relative concentration of these solutions. There are 10 silver ions in that first beaker. However, there are only 5 magnesium ions in that same volume, that 1 liter volume. So we can conclude from the particle diagram that the concentration of silver is twice as much as the concentration of magnesium. So the correct answer is either C or D. Now in terms of volumes, we are combining 1 liter of each solution to form 2 liters of total volume at the end. If the magnesium, which is the spectator ion, is still present in that final beaker, beaker Z, but there's twice as much volume, we are cutting the concentration of magnesium by half. So therefore, the correct answer is D, which shows 0.5 molar magnesium nitrate in the final beaker. Question 6, we have to decide what this substance is in terms of it being an electrolyte or an acid or a base. Let me call your attention to page 118. It talks about weak electrolytes, and the first example they give is CH3COOH, which you know as acetic acid. The structural formula of acetic acid is drawn, and you can see that it looks very similar to the structure in number 6. So if acetic acid looks like that, the molecule we have is called propanoic acid, but it has that same COOH functional group that makes it an acid. It is a weak acid. It is a weak electrolyte. In question 7, we have to decide which statement is true about hydrofluoric acid, HF. Table 4.2 lists the strong acids, but hydrofluoric acid is not on that list. So therefore we know that hydrofluoric acid is a weak acid. Now the question is why? On page 118 it says we must be careful not to confuse the extent to which an electrolyte dissolves with whether it is strong or weak. And they give acetic acid as an example of a very soluble compound, but does not dissociate completely. So the correct answer is that hydrofluoric acid is a weak acid, not because it's not soluble, but because it is only partially ionized in water. Question 8 is talking about a reaction between solid calcium carbonate and a solution of hydrochloric acid. Because it says solid calcium carbonate, that means that the correct answer is either A or B or D, but it could not be C because they're showing aqueous carbonate ions. As far as other wrong answers to eliminate, we can eliminate choice B because it has calcium chloride written together and not separated. It also doesn't have enough oxygens on the right as it does on the left. Now, in terms of carbonates reacting with acid to produce carbon dioxide gas, you can read about this on pages 129 and 130 in your book. We're going to produce water and CO2 when carbonate reacts with acid. So the correct answer is A. And you can see that the problem with choice D is the same problem as choice B. There aren't enough oxygen atoms on the right side of the equation. In number 9, we have to write a net ionic equation for a weak acid, acetic acid, with a strong base, potassium hydroxide. A weak acid should not be broken up into ions, but a strong base should be broken up. So in terms of the 4 choices, if we know that acetic acid is a weak acid, we can eliminate choices A and B. And because we know that potassium hydroxide is a strong base, the correct answer is C. The spectator ion potassium was crossed off on both sides of the equation. Number 10 is talking about, is it a redox reaction or not? And if it is, what element is being oxidized and what's being reduced? Let's assign the oxidation numbers for the elements on both sides. Silver is an element, so it is 0. And in H2S, H is +1 and sulfur is -2. On the right, silver now is part of a compound, silver sulfide. Silver now becomes +1, and hydrogen is 0 because it is in elemental form as hydrogen gas. Sulfur did not change, so the correct answer is not A. Hydrogen is going from +1 to 0, but that is reduction, not oxidation. So the correct answer is C. Silver is changing from 0 to 1, which by definition is oxidation. Number 11, we have to decide what is changing. In this case, let's go ahead and assign the oxidation numbers for everything on both sides. In KMnO4, potassium permanganate, K is +1, manganese is +7, and oxygen is -2. Oxygen will still be -2 in the next compound. Sodium is +1, and sulfur is +4. That compound is called sodium sulfite. We have water, which is just +1 and -2 for hydrogen and oxygen. Now we have manganese, Roman numeral 4, oxide. So the manganese is changing. Sodium sulfate, we have a different oxidation state for sulfur because now we have an extra oxygen in that formula. So sulfur was +4, now it's +6. And potassium hydroxide, everything is the same. +1 for potassium and -2 for oxygen and so forth. So what's changing? Manganese is going down from 7 to 4, and sulfur is going up from 4 to 6. So sulfur is being oxidized, manganese is reduced. Number 12 can be a problem you'll see on the real quiz. So you should be able to comfortably assign oxidation numbers for all of the elements in a particular compound. So it's a good skill to practice, assigning oxidation numbers. Let's go ahead and start with choice A. Carbon's -4, hydrogen is +1. For CH3OH, carbon now becomes -2. And the other elements are still +1 and -2. So in all of these choices, hydrogen is +1, oxygen is -2. It's the carbon that might be different. So the correct answer is going to be one in which carbon is the same for each substance, same oxidation number. The next example, CH2O, carbon has an oxidation state of 0, but with CO, carbon monoxide, it is +2. C2H4, carbon comes in at -2, but C6H6, carbon is -1. So hopefully letter D is the correct answer. And yes, we can see that carbon has a +4 oxidation state both in carbonic acid, H2CO3, and in carbon dioxide. So correct answer is D. And now the last multiple choice question. Let's look at our activity series. If a metal does not react with cobalt ions, that must mean it is less reactive than cobalt. So it must be below cobalt on the activity series. If a metal does react with H+ ions, an acid solution, to produce hydrogen gas, then it must be that the metal is more reactive than hydrogen. So it must be above hydrogen. So the answer could have been either nickel, tin, or lead. Correct answer is tin. Okay, here is our first free response question. We have a diagram showing a water molecule, and we have a diagram showing a portion of the lithium chloride crystal. Now, in terms of which circle refers to which ion, you should know that in terms of electrons, lithium plus has a total of 2 electrons, whereas chloride minus has a total of 18 electrons. So the smaller circle is supposed to represent the lithium cation, and the larger circles are supposed to represent the chloride anion. In your textbook on pages 117 and 118, you can see that the cations are attracted by the negative end of water. So the oxygen portion of the water molecule should be pointing toward the cation, and then the anions would be attracted by the positive end of the water molecule, so the hydrogen portion should be pointing toward the anions. And we've seen these diagrams before. So here is my lithium cation labeled with its symbol and charge, and I'm pointing the negative portion of the water molecule toward the cation. And there's my chloride ion, again symbol and charge, and I'm arranging the water molecules so that the hydrogen end points toward the anion. So that's what the diagram should look like. In terms of how many water molecules you draw, I would say you should draw at least 2 water molecules to show that you know what you're doing. The next question says, is lithium chloride a strong, a weak, or a non-electrolyte? Well, hopefully you know that because you separated those ions, lithium chloride disperses its ions throughout the solution. It completely dissociates, so it should be classified as a strong electrolyte. Free response question number 2 is going to ask you to draw 2 molecules of methanol in water to show what they would look like. So a molecule of methanol would look something like this. I just drew a carbon bonded to 3 hydrogens and then bonded to oxygen followed by another hydrogen there at the end. Now if you decided to draw these as with lines connecting them, that's fine. As long as it looks like covalent bonds, that's fine. On page 117, you can see that a molecular substance like methanol or sugar will dissolve but not form ions. The molecule stays intact. So your diagram should have shown 2 intact methanol molecules with no charges or ions of any kind. So in part B of this question, we have to classify methanol as a strong, weak, or non-electrolyte. Clearly, molecular compounds in water, even though they dissolve, they do not produce ions. They are going to exist as intact molecules. So therefore, methanol should be classified as a non-electrolyte because it is a covalent or molecular compound. It does not behave as either an acid or a base. So non-electrolyte. For part 3, we have a bunch of net ionic equations to write as well as molecular equations. Nickel Roman numeral 2 bromide is written as NiBr2. Barium hydroxide is written as BaOH parentheses 2. And we're going to produce nickel hydroxide and barium bromide. When we consult our solubility rules, it turns out that the nickel hydroxide is the precipitate. So we write nickel hydroxide as the product, and then we show the separate ions on the left side of the equation. Notice we have a 2 as a coefficient to balance the number of atoms and the charge. In part B, we have copper Roman numeral 2 chloride, so written as CuCl2. We have ammonium sulfate, which is written as NH4 parentheses 2 SO4. The 2 products you would produce would be copper sulfate and ammonium chloride. Now when we look at the solubility rules for these 2 compounds, we discover that both of these products are soluble. So there is nothing else you have to write except no reaction. There's no precipitate formed, so there is no reaction between these 2 soluble materials. All they do is they make 2 new soluble materials. In our next example, we have a weak acid reacting with a strong base. So propanoic acid, which we saw before on the multiple choice questions, is written exactly like that. And sodium hydroxide, NaOH. The acid will lose its H, so it produces water, and we get the sodium salt of propanoic acid. We get sodium propanoate. Now we have to decide, do we split these up or do we leave them together? A weak acid is not broken up into ions, so we just leave that formula alone. A strong base is broken up into ions, and the sodium becomes eliminated as a spectator ion. So we have propanoic acid plus hydroxide produces water and the propanoate ion. Now we have a reaction between a strong acid, so nitric acid, HNO3, and a weak base, methylamine. The proton transfer, the H plus, will go from the acid to the base. So we end up getting CH3NH3 plus, the methylammonium ion. And then we have nitrate NO3 minus. So that salt is right now written as one formula, but it's going to be split up into ions so we can understand what's going on. I'm only going to write H plus because it's a strong acid. I'm going to have to write the entire formula for methylamine, and I can eliminate nitrate ions on both the left and the right. So we have the methylammonium ion with its positive charge. So strong acid and weak base to produce that positive ion, the methylammonium, CH3NH3 plus. Now in part E, this is potentially a redox equation, oxidation reduction. Aluminum is just by itself, just aluminum, and we have zinc sulfate, ZnSO4. If this reaction occurs, I'm going to get aluminum sulfate, Al2 parentheses SO43, and then just zinc by itself. Let's see if aluminum is higher than zinc on the activity series. Okay, so yes it is. That means that aluminum is oxidized more easily than zinc, so this reaction does occur. We still have to balance it. Let's go ahead and put in some 2's and 3's to make sure it's balanced. And the net ionic equation is going to split up the ionic compounds, zinc sulfate and aluminum sulfate. Since sulfate is a spectator ion, we still have aluminum ions and zinc ions. We have to make sure that the equation is balanced. Your net ionic equation just focuses on the metals, but it does not include sulfate because it's soluble on both sides of the equation. And then we come to chromium metal, so Cr, reacting with magnesium nitrate. Let's see if chromium is above magnesium on the activity series. No. Chromium is below, which means chromium is less active. Magnesium, unfortunately, is not going to give up its electrons to chromium because it's already a +2 charge. It can't lose any more electrons, and chromium cannot lose its electrons to magnesium. So as a result, this is no reaction for this example. We have to decide if number 4, it's a redox or not, and if it is, what's changing? So Fe2O3, iron is +3, oxygen is -2. Carbon monoxide, carbon is +2, oxygen is still -2. On the right side of the equation, iron is 0 as an element, and carbon is now +4. This is a redox equation. Carbon is being oxidized from +2 to +4, and iron is being reduced from +3 to 0. All right, in part B, let's take a look at the oxidation numbers for all these elements. Potassium +1, sulfur +4, oxygen -2. Hydrogen +1, bromine -1. On the other side of the equation, nothing is changing in terms of hydrogen or oxygen. Sulfur is still +4, and potassium and bromine are not changing as well. So this is not an oxidation-reduction reaction. All right, well, that wraps up the answers and explanations for this practice quiz. I hope that this was helpful to you. Good luck studying for your quiz.